So thanks, Giovanni, for the nice introduction. Thanks to all of you for being here. It's really a pleasure for me for having the opportunity of introducing myself and tell you something about one of my line of research. I am a computable theorist. I work in computability theory. That said, at least for this talk, I will not assume any prior knowledge in mathematical logic. I will try to give you at least kind of a broad perspective of this line of research, which aim of combining computable structure theory together with algorithmic learning theory. Of course, I will give you definitions for both of these area, and we will see how we will reach, how we will answer to our motivating question, which is to develop a formal framework which allow to make sense of the idea of learning an algebraic structure. Okay, so whatever I'm saying today, it's joint work with my colleague in Vienna, Katerina Fokina, with Nikolai Bajenov from far away in Siberia, Sobolev Institute of Mathematics, and with Timo Koetzing from University of Potsdam in Germany. Okay, and feel free just to interrupt me for any clarification or remark or whenever, I mean, you feel that it would make sense. Okay, so let's start with a game, right? So I would like to use this a game as a way to have you some of the ingredients, the main ingredients of our framework in the background, right? So even for the moment, I mean, just try to have this sort of intuition, and then of course everything will be formally clarified, right? Now, suppose what you are looking at is a copy of a structure, right? And the only thing that you know beforehand is that this structure can be either the order type of the natural numbers, right? Or the reverse order type, right? Either it behaves as the positive integers or it will behave as the negative integers, right? And in logic, we denote the order type of natural numbers by the ordinal omega, and the reverse ordering, the one of the negative integers with omega star, right? Now, your task, it is try to guess at any given stage, try to guess which one of the two linear orders this copy will be isomorphic to, right? So basically, at some stage, you see only two dots, right? Of course, locally speaking, this fragment can be obviously extended with respect to both this structure, can eventually be extended to be a copy of omega or omega star. And yet, at any single stage, you have to guess which one of the two eventually will it be, right? So, for instance, you see like some dots, right, to the right, the structure is extended with a new greatest element. So you might say, well, it's behaving closely to omega. And in fact, I mean, you're looking at more and more elements. You see that this order type might resemble the natural numbers, right? So you might say at this stage, well, perhaps this is omega. And you go like that until you realize that there is another least element. And so perhaps it will be, in fact, omega star. And that's it, right? Now, the question it is whether you can eventually stabilize to a correct conjecture, whether there exists an algorithm such that provided with any possible copy of either omega or omega star is able, after finitely many stage, to stabilize to a correct conjecture of which of the two structure the target structure is isomorphic to, okay? So, and then you can formulate other questions about other pairs of structures. So what about comparing omega with z, the order type of the integers, etc., right? Try to think in your mind of this example, and now I will slowly go to the formalities. So first of all, algorithmic learning theory is about induction. It's an attempt to do a logical framework for induction. Roughly speaking, induction, which is in a sense dual to the notion of deduction, induction goes from the effects, always just a finitely many of them, possibly a finite sequence of effects, to causes, right? So somehow it's really the opposite, I mean, of deduction. Deduction, it is, of course, the cornerstone of classical logic. You typically have your axiom, then a deduction operator will tell you which theorems you can derive from this axiom, right? In induction, you basically do vice versa, right? Now, what is interesting, it is that historically speaking, induction has a very bad press in logic, right? There is a sort of intuitive recurring idea that you cannot really do a logic for induction, right? Induction is not really enough reliable to do a mathematical reconstruction of what induction is about, right? And this idea dates back even to the ancient Greeks. The Stoics got this intuition that, well, incomplete induction only draws uncertain conclusions, right? Since, of course, any new observation can falsify the current thesis that you are able to extract from finitely many observations. On the other hand, complete induction, if you see all instances of a domain, certainly you can make a universal statement, but then only in a vacuously trivial way, right? So when the induction is incomplete, it's not reliable. When it is complete, it's useless, okay? Now, there is an old philosophical argument that goes back to Hume, which says basically similar to this, that induction cannot be conceptually justified. A classical curve fitting paradox due to Bernoulli, right? If you have a finite number of points, right, you can always find infinitely many interpolation for these points, right? Infinitely many curves that go in through them, right? So extracting from finitely many points what's the curve that is actually interpolating them without adding any additional constraint is an ill-founded problem, right? You always have infinitely many possible options for this. And then, I mean, there is famous story of Russell about a turkey, right, that tried to produce an induction from observing that any single morning at 7 a.m., the farmer is providing the turkey with food, no matter of the meteorological condition, no matter of which day is. Any single morning at 7 a.m., the farmer is coming with some corn food for the turkey. So eventually the turkey, after observing enough observation, just formulate its universal statement, which is at 7 a.m., any single morning, the farmer come with corn food for me, right? But of course, eventually that very morning, it was the Thanksgiving day, and the farmer come and just break the neck to the turkey, right? So basically, all of that are stories for which the idea is induction is not really reliable. You cannot do logic of induction. You can certainly not do a mathematical reconstruction of induction. Now, on the other hand, we have the empirical observation that inductive inferences are widespread, and they are very much successful, typically. And the point is twofold. So all the skeptical arguments against the reliability of induction assume these premises. So first, you never allow mistakes, right? A single mistake is enough to invalidate an inference, an inductive inference. Sorry, here's a typo. And so this contrasts with the fact that inductions often provide knowledge only in the limit, right? Okay, so think of this image of a scientist which is trying to recover a law from finitely many observations, right? A physicist is observing instances, finitely many instances of a certain phenomena, and is trying to guessing a governing law, right? Of course, this would be a trial and error process which provide knowledge only in the limit, right? And on the other hand, the universe, or if you prefer the data set in skeptical arguments, does not collaborate, to the point that the failure of an inductive inference is always provided in the worst case scenario, right? So this opened the door to the idea that you may possibly develop a formal framework for induction if you relax these two conditions. If you allow your conclusion to be obtained in the limit, right, to provide knowledge in the limit, and on the other hand, if you, rather than looking at the worst case scenario, you kind of look at a sort of average case scenario. And we will see a way to formalize this, okay? Now, algorithmic learning theory, which is the field to which this talk contributes, it dates back to the work of Gould and Putnam in the 60s, and it develops to a really big branch of at the interface of mathematical logic and computer science. And nowadays it provides different formal methods for the inductive inference, right? Now, generally speaking, the idea of all this field, it is the question of how a learner, right, some agent, and we will see that our formalization of an agent is typically a Turing machine, typically an algorithm, how an agent provided with more and more data about some environment is able in the limit to achieve some systematic knowledge about that, right? Now, of course, all of that it is very much informal, but I will come to formality. Let me first give you one example, a really intuitive one. So suppose you see more and more outputs of a function, right? And this idea is that this function is a timed sequence of observation of a given phenomenon, right? Assume, for instance, that you are a molecular biologist. You would like to know the rate of growth, you would like to guess the rate of growth of a given population cell, right? So you leave the cell, let them multiply, and then come back and with any 24 hours and number them, right? So abstractly, what you have it is that you have a function, and what you see of the function are just the outputs, stage by stage, and you would like to know what is the program which is generate this function, right? I will come back to this idea of program, which is a crucial one, right? But intuitively speaking, you're looking at all outputs of function, and you would like to try to guess what's the corresponding program, right? What the function is. So for instance, you see that F1, it is 2, right? Of course, remember curve fitting paradox, you have infinitely many options for that. So for instance, you might guess that the function, having observed only this first output, might be the constant function to 2, right? Maybe it's the function that for any single input, it will give you as an output 2, right? Next, you see the next output, and in fact, F2 equals 4, right? And so you have to revise your conjecture, right? It cannot be anymore the constant function to 2, so you might guess it's the double function, right? Now you see the third output, and unfortunately, you again have to revise your conjecture because F3 it is 8, right? So you might say, okay, maybe it is the exponential, but then you see that F4 it is 11, right? And then you try to give another guess, right? For instance, you might say, okay, it's the function that for the first 3 values behave as the exponential on base 2, and then eventually become the constant to 11, et cetera, et cetera. So the main question in algorithmic learning theory is try to understand in which cases you have an algorithm that's stabilized to a correct conjecture of what is the program generating a given function by looking at the outputs of this function, right? So fairly intuitive. So most work in algorithmic learning theory deals with 2 main paradigms. So the first one aimed to represent the idea of a scientist learning a physical law. And mathematically speaking, this is rendered by the idea of learning total functions, similar to what we see, right? You have a family of functions. For each function, you are looking at the outputs stage by stage. Let's say function domain, the natural numbers. You're looking at outputs stage by stage, and you would like to have an algorithm which uniformly for all the functions in the domain of functions you would like to learn is able to output the correct program which is computing these functions. Okay. So of course, in this case, the order in which the data is presented matters, right? If you permutate the value of the function in different inputs, you obtain a different function. There is another classical model, which is language acquisition, right? And this idea, it is learning regular languages. And in this case, order does not really matter. You have a set, you have all possible enumeration of these sets, and you would like, from looking of these various possible enumeration, to consistently stabilize to a correct conjecture of what is the set itself, having observed only finitely a larger subset of the set. Okay. So Now, these paradigms are at the basis of a very large body of work. There is an enormous literature in algorithmic learning theory, and yet they are very good to learn unstructured flow, right? But very much typically we have information which is structured, right? Think of algebra. In algebra, we constantly deal with sets on which we define operations or relations, right? So the idea is how to learn data having some structural content, how to learn a graph, how to learn a group, a ring, etc., etc. Okay. Now, there has been some previous work about that, right? So, for instance, Frank Stefan and his school, they started giving a certain algebraic structure how to learn some information about the structure itself, right? So, for instance, in this paper with Vensov, what they have it is you have commutative rings and you would like to learn ideals of them, right? So you fix a sort of algebraic structure and you would like to learn in the limit information about algebraic information about that. You would like to extract this information from the copy of the algebra you're looking at. Okay. Now, our goal here, it is more general. So we would like to combine the technology of algorithmic learning theory with notions coming from computable structure theory, which is our main field of study, to develop a general framework for learning the isomorphist type of structures. So we'd like to make sense of the idea that you are looking at larger pieces of a given graph, let's say, and you would like to eventually stabilize to a correct conjecture of what the graph eventually will be. What will be the isomorphist type of the graph? Okay. So we have two constraints, right? So first of all, to learn the isomorphist type of a structure, well, you must be able to name this isomorphist type, right? You must be able. This basically applies also to the case of function, right? Also for the learning of total function. Suppose your function is generated by some random process, right? It's a function whose range will be 0 and 1, and is generated by coin tosses, right? If you have a function like that, a random function like that, typically you will not have a way of compressing this function in a finite description, right? It's just randomly generated, right? So if you would like to look at that from a basic set theoretic point of view, you have only countably many names, but of course you have continuum many functions from the natural numbers to the set 0, 1, right? So first of all, what we needed is to restrict our possibility of learning to function that possesses name. And the straightforward way to do that, it is by restricting the case of to the case of computable structures, right? So the name of a computable structure will be the code of a Turing machine that computes it, right? And remember that a structure is computable if you have that all relations and operation on that structure are computable, right? So for instance, a graph is computable if for any two vertices you have an algorithm which infinitely many steps will tell you whether there is an edge between these two vertices or not. Okay. So the second constraint that we have here, it is that we'd like learning to be independent from the way in which data is presented, right? So relative to structure, we'd like our learning to be successful no matter which isomorphic copy of the structure you consider, right? So as I said, a successful learning procedure must work for all isomorphic copies of a given countable structure. Okay. Now let me give you a few preliminaries before providing you with our definition of the framework. So first of all, our structure F domain the set of natural numbers. This is an assumption that it happens all the time in computability theory, in computable structure theory. Basically, first of all, on the one hand, you would like your domain to be countable, right? So classical computability theory deals with countable objects. On the other hand, you don't want to assume a countable set, an arbitrary countable set, because you don't want to have some hidden complexity in the choice of the domain, right? So you choose the natural numbers, which are very well behaved from the effective perspective, so that all the complexity will come from the relations and operations you consider, right? So all the structures have the domain, just the natural numbers. Now with this notation, with just a note, that's quite classical notation, the substructure of the structure having as the domain the first n natural numbers, right? Now structure A is a copy of B if A and B are isomorphic, right? And as I already mentioned, a structure is computable if all relations and functions are computable, okay? So here's an example, right? You have three graphs which are pairwise isomorphic, right? They're copies of each other on the alphabet A, B, C, D. Okay. So, and basically the intuition, which I will describe in the next slide, it is we'd like to see of larger and larger pieces of a given structure, of a target structure, and we'd like to the learner at any stage to try to guess what will be the eventual shape of the structure is looking, right? What will be the isomorphous type of that structure, right? So basically, we have to specify these ingredients. So first of all, we have to say what is the learning domain. And the learning domain will be the collection of all copies of a family of computable structures K. Remember, we want our learning procedure to be independent from the way in which data are presented, right? Which is why we consider all possible isomorphic copies of the structures to be learned. Then the hypothesis space will just consist of the names of the possible conjectures that the learner can formulate, right? These are just names for the structures. As I mentioned before, will be code for Turing machines that compute the structures, okay? And the learner is just a map, right? Notice that from this high-level point of view, we don't assume this map, we don't put any effective constraint to this map, right? We don't even require this map to be computable, right? Eventually, we'll say a few words about that when we have this additional constraint. But for the moment, the learner will be just a map from the learning domain to the hypothesis space, right? Just a map that looking at any fragment of a substructure of an isomorphic copy, arbitrary, of the structure to be learned, always produce a conjecture on the isomorphous type of this structure, right? So just a map. And a learner receives all positive and negative information about any structure in the learning domain, right? So if you're looking to a graph, larger and larger subgraphs of this graph, for any single vertices, you will know eventually whether there is an edge between them or the edge is missing, right? And eventually we have to specify our condition of when a learning is successful. We say that it's successful if it eventually stabilizes to a correct conjecture, right? So a little bit more formally, let K be a family of structures with some uniform enumeration of all the computable structures from K, right? So we have these collections of structures, M sub I. So a learner M is just a function mapping all fragments, right? All substructures of any of those structures, right? From the family you would like to learn to the set of conjectures. We also allow the symbol question mark, which allow the learner to postpone his conjecture, right? But eventually it will be obvious that this question mark can be used only finitely many times, right? And this is because we say that the family K is learnable if there is a learner, if there is this function from the all the substructures of the structures from K, right? Such that for any possible of this structure A chosen from this family of structures K, you have that there exists a stage at which the conjecture stabilizes, right? There exists a stage such that at this stage, the learner guess that the structure has isomorphous type E, right? So he guessed that the structure, it is isomorphic to ME, right? Which is one of the computable structure from this collection, and he never changed mind, and this is the correct conjecture, right? So morally speaking, what we're saying it is that L learns any computable structure from K, right? So in the limit, it is able, looking at any isomorphic copy of a structure from K, to learn its isomorphism type. Okay. Now notice that if K contains only one isomorphism type, if K is only one structure, right, can be, for instance, I don't know, a copy of a complete graph on the natural numbers, right? For any two natural numbers, there is an edge between them, right? Now, if it is only that, well, certainly there will be a learner for this. Notice that here, this existential quantifier, there is a learner, right? Can be any sort of learner, right? So certainly if you have that your family consists of only one isomorphism type, there will be a learner that just constantly output this isomorphism type for that, right? So trivially learning that family. So family with just one isomorphism type are trivially learnable. Interestingly, if you already go to family consisting of two distinct isomorphism types, well, you have both example of learnability and no learnability. Let me show you examples. So tell me if you have questions, remarks. I will go to example now if you need them, but this is a good point to have any kind of clarification question. Okay, good. So let's have a look to our first example of learnability, right? So suppose that A and B are what we call equivalent structures, right? So these are just structures on the, remember that all our structures are defined on the natural numbers. So these are just structures with domain the natural numbers on which we define an equivalent solution, right? So A consists of infinitely many boxes, infinitely many equivalence classes of a given size. B will consist of the same of equivalence classes of the same size together with a bigger box, right? A bigger equivalence class. And we'd like to show that this family is learnable, right? So provided with any copy of either A and B or B, we have a learner that is eventually able to stabilize to a correct conjecture of one of which will be, right? So basically, let's define this learner L, right? So you're looking at this structure S, right? S, for the moment, it is only one box, right? The only thing that you know it is that eventually S will be either isomorphic to A or isomorphic to B, right? And you would like to offer a procedure by which eventually you will guess which one of the two cases will be, right? Now, of course, the learning procedure, it is trivial in this case. The idea is, well, you constantly output that is A. You believe always that it is A, right? Unless at some stage you see that S, that one fragment of S produced the bigger box, right? What we call the separator, the B separator, which is in B, but is not So as soon as you have this B separator, you immediately know that this structure cannot be extended to a copy of A, right? Because the B separator cannot be any part of A. And then you change your conjecture from A to B, and then you are able to know B, right? So in this case, you know that there is a learning procedure, so the family AB is learnable. Also, you know that it's learnable with at most one mistake, right? So let's see a slightly more delicate example of learnability, which is really resembling the starting game that I given to you, that of trying to learning omega versus omega star. So suppose you have two structures A and B, right? And now still they are equivalent structures. So you have infinitely many boxes of the same size for A and B, and then two smaller boxes, an A separator and B separator, both of them are smaller size than the infinitely many boxes that are shared by both A and B. So what's the idea here? Well, let's try to build this learning procedure, right? Having looked at only this fragment S at this stage, you have no reason to prefer between A and B. So suppose you just choose one of the two, let's say A. right? Now, you continue guessing that is A, unless at some point you see that you have a B separator, in which case, obviously, you would like to switch to B, right? Now, the problem here it is that what can happen it is that a B separator, in fact, will be extended to be one of the boxes that also A contains, infinitely many of those, right? So the problem it is that this fragment, which locally looks like B, can actually evolve to be an initial segment of A, right? In which case, what you do, well, you switch your conjecture and you switch back to A, right? And now the idea it is that you basically go back and forth switching between A and B, but the trick it is that eventually at some stage, the structure as you're looking must show up either the real A separator or the real B separator, in which case you eventually converge to the correct conjecture. So this is a case in which you know you will be able to learn any isomorphic copy of either A or B, so the family AB is learnable, but you don't have a bounded number of mistakes, right? You make arbitrarily many mistakes, but of course always finitely many. So let's have a look now of an example of non-learnability. So first of all, how to prove non-learnability? If you prove learnability, well, the idea is just to offer a learning procedure. So formally speaking, you just define an algorithm for that, right? Of course, here in this presentation, I'm avoiding a lot of technicalities, and formally speaking, you really would like to specify the algorithm itself. But for cases of non-learnability, well, it suffices actually to specify a copy S of either A or B, such that you know that no learning procedure can actually satisfy that, right? So the strategy is like that. Towards the contradictions, assume that a learner learns the family AB. The idea is constructed by stages a structure S will be part of the learning domain. So eventually will be a copy of A or a copy of B. You don't know which one of the two. The construction of S will depend on the information that you would like to diagonalize against, such that L necessary phase to learn S. So let's see how to do that. So to some extent now the situation is reversal. What you have it is that you are constructing this S in such a way that eventually you would like the learner, which is given, to fail to guess this, right? Now, and the only constraint that you have to satisfy it is that necessarily S eventually must be either isomorphic to A or isomorphic to B, okay? So you're looking at this and you're seeing that the learner is currently conjectured that you have A, right? In which case, of course, you will build your structure as being isomorphic to B, right? So you continue to build that isomorphic to B, right? Waiting for the learner to switch his conjecture and say this is B. If the learner never do that, you win, obviously, right? As soon as the learner switches conjecture and say, well, this is B, what you have it is you put here an A separator, right? And then eventually you continue your construction to make it as A, right? Forcing the learner to change his mind. And then eventually you have two possibilities. Either the learner at some point stop change mind, in which case you correctly diagonalize against him, right? Suppose that the learner continuously say, looking at more and more fragment that this is B, then you win because your construction plan it is to make it isomorphic to A, right? Now, the other case it is, well, the learner tried to constantly follow you, right? So anytime you force the learner to change his mind, he would follow changing his mind. But then if he does like that, he would change his mind infinitely many times, and then the learner is not successful, right? Remember that the learning is successful if it is stabilized in the limit to a correct conjecture, right? So in both cases, you win. Okay. So back to the starting game, really briefly. So we have that the pair structure omega and omega star is learnable. So although at each finite stage, fragments of omega and omega star can actually resemble each other, right? Can actually be, any finite fragment of omega can be extended to a copy of omega star and vice versa. What we have is that at some stage, the copy target structure will show either the true least or the true greatest element, and then eventually you will stabilize to a correct conjecture. On the other hand, the superstructure omega and z, where z it is the order type of the integers, it is not learnable, right? And basically for a reasoning quite similar to the example of no learnability that I gave it to you. Okay. Now, basically, we provided in two different papers, actually, a characterization of this notion of learnability in two different ways. So one providing a topological characterization for that, and in the other paper providing a model theoretic characterization of learnability. I will say a few words about this second characterization. So our main result is a full characterization of which family of structures are learnable. And really roughly speaking, what we prove it is that a family K is learnable if and only if the structures from K can be distinguished by formulas of a certain logical complexity, right? Now, of course, this expression of a certain logical complexity means nothing, right? And now I can try to give you at least of one idea of what I mean about that. Please tell me maybe how much time do I have left?
Yes, so you have 10 minutes, so yes, you can continue.
Okay, thanks for that. Okay, so I will briefly tell you about this, our main logical result about that, right? Now, to do that, what I need to you it is just a little bit of formalities, right? And to introduce you to the logic L omega 1 omega, right? This is an extension of first order logic in which you are allowed to have conjunction and disjunction of infinite set of formulas, right? Of course, in first order logic, when you have conjunctions, these conjunctions can range only on finitely many formulas, not like that in L omega 1 omega, right? Now, this is particularly powerful, this infinitary logic, because it is allowed to capture many natural mathematical concepts that first order logic it is too weak to represent. So for instance, I mean, suppose you would like to say that a group is torsion, right? Now, to say that, well, basically what you would like to say it is that if you take any element in the group, its order will be finite, right? So if you multiply this element by itself, if some number of times, but finitely many, eventually you will go to the identity, right? Saying this information, right, that it must be the case that either x is equal to the identity itself, or x times x is equal to the identity, or x times x times x it is equal to the identity, etc., for any possible power of x, it is an infinite disjunction, right, of formula. So being torsion for a group, it is a property that you cannot express in first order logic. You can do that within L omega 1 omega. So we have a way of stratifying the complexity of formulas in this infinitary logic. So we say that formulas sigma 0 infinitary and pi 0 infinitary are formulas, classical first order formulas with no quantifiers at all, right? So atomic formulas, if you want, right? Boolean combinations of atomic formulas, in fact. And then I will just give you a brief intuition for that. We say that a formula belongs to the level sigma 1 of this hierarchy of infinitary formulas if it can be expressed as a countably infinite disjunction of formulas, right? And then it will belong to the pi 2 level if it is a countably infinite conjunction of sigma 1 formula. This is what we do always in logic, right? We recursively define any single hierarchy, right, by specifying at some level what elements will belong to this level, referring to the previous level, right? So basically, I mean, the only intuition you have to keep in mind, it is that this is a non-collapsing hierarchy of formula which classifying them according to their complexity, right? According to their logical complexity. Now, the theorem that we have it is that for all families of computable structures, we have that these two conditions are equivalent. The families is learnable, and this is exactly the same of being able of separating this structure by sigma 2 infinitary formulas, right? So formula of lying at some level of complexity in this infinite hierarchy, right? So basically, the idea is if you are able to syntactically separate this structure by using formula of that given complexity, then what you have it is learnability, right? And this is an if and only if. Okay. So this is a full characterization. The proof is quite delicate. It uses some advanced technique of computable structure theory, which is called Turing computable embeddings. I would say nothing about that. Let me just briefly conclude that what is fascinating is that by this theorem, we can obtain through some additional work, we can show that learnability is very much sensible to the algebraic information of the families to be learned, right? So we can show that there is an infinite learnable family of distributive lattice. We can show that the same is true. We can show that the same is true for P groups, right? But what we have is that no pair of Boolean algebras is learnable, right? If you add more structure there, you immediately fail this learnability power for this family. On the other hand, we have that there is no infinite family of linear orders, which is learnable, but for all n, there is a learnable family of exactly n linear orders, right? So basically, the algebras you consider will be very much different with respect to this learning power. Okay. Maybe I will really briefly conclude with that, right? So one obvious extension to this work, notice that we said that the learning is just a map, right? Now, since we are computable theorists, we'd like to say, okay, but what happens if you add some effective constraint to this map? What if you ask that the learning is a Turing machine? What if you ask if the learning is a computable function, right? Maybe I'll just quickly skip this, right? So one natural guess would be that if K is easy to be enumerated, right? If K, for instance, consists of only finitely many isomorphism type, if it is a finite family of structure, well, if it is learnable, it must be the case that it's learnable in some effective way. It's learnable by Turing machine, right? A natural guess would be that if it is learnable, there is a computer program to learn it. We showed that this is not the case, right? We proved that there is a uniformly enumerable family which is learnable, but no computer program can learn it. And in fact, we proved that you can do the same even with a family consisting of only two isomorphism type. There is a family of structures absolutely non-natural, very much artificial and complicated. They're really convoluted structures, but for which there is a learning procedure. So they are learnable in our framework, but no computer program can learn them. Let me actually conclude with further directions. Some of them we are currently exploring. Some other are just open. So if you are curious about that, I would be happy to speak with you about this, etc. So for instance, you can assume that the learner receives only positive information of the target structure. So if you have the two vertices in the graph have an edge between them, you will know that, but you will never receive the information of the non-existence of an edge, right? Or you can force the learner to make no mistakes, right? So this additional constraint, and then ask, or maybe just a fixed bound number of mistakes. And then you see how the learning framework would be modified by this additional constraint. Or you can think the learner to be aided by some external source, a teacher if you want, or as we call them in computability theory, an oracle. So you have some external information that feed the learner with some information and then see how the learner is affected by this external source of information. Or you can assume that a team of learners cooperates, right? So asking how much the learning power expands if you allow n learners to cooperate with each other? Or what about probabilistic learning, right? Or to name the project we are currently working on the most, there is a way of giving a topological interpretation of all of this, right? I will not say much about that apart from this. Now, in this topological interpretation, it's easy to see that our learning paradigm is just continuous, right? So basically, as we define this idea of providing a conjecture from the substructure of a given structure, it is naturally represented with the idea that we are dealing on continuous functions on Cantor space. In fact, what if you allow the learning to be non-continuous? What if, more speaking, you allow the learning to make questions now to the complete diagram of the target structure? Not only the conjecture should not only be limited to the fragment you're looking, but looking at this fragment can make some question about the overall structure itself, right? And then you have a completely different world, right? So I'll stop here. If you're interested, we have 2 papers published on that and another one just submitted. Okay. So, and I would like to conclude with that, right? This is a recurring strip that you have in the Peanuts, right? So basically here Charlie Brown is trying to solve a learning problem, right? Whether Lucy eventually will keep for at least one time to keep the football ball on the ground, or again, if she will just raise it up and Charlie Brown will fall. Okay. And that's it for me.
Okay, thank you, Luca, for this nice talk. So I would like to ask to the audience if there are any questions or comments.
Yes, I have one, but I cannot see my face. I don't know why. What should I do? Should I do? I don't know how to. Okay, anyway. My question is that Luca, you say that this theory, mainly you use to let computers learning how to learn, right? Or
yeah, essentially, yep.
Exactly. I mean, it's just as big applications from the point of view of computer learning, automatic learning. And another thing is that if not in special case your theory, but similar theories have been tested indeed to find the right conjectures, as you explained to us. I mean, you have the concrete examples, for instance, that just to give an example, yeah, for even a toy example, for instance, as you mentioned to us, trying to guess what kind of sequence we have once we know the first 20 or 30 values. Have you tried some?
Okay.
Even by computer, I mean.
Yeah, sure. So directly, I didn't. The fact is, okay, I will answer in 2 ways. So first of all, basically, the learning procedure we provide in the paper are algorithms themselves, so are quite easy to be implemented. What I know it is that some kind, for instance, of some kind of learning, it is of this sort, really, this kind of trial and error deterministic learning has been applied to learning underlying graph of social networks of any kind. So for instance, you see like the friendship graph in some fragment of Facebook, and Facebook is interested to know at some stage eventually how it will evolve. And typically the kind of strategy that they implement are fairly similar to this. Notice that a really big difference here, it is that even though, of course, all of these has potentially many applications, our work, it is really on the foundations, right? So in particular, it is really dealing with infinite structures. So it's basically more, we have much more application with standard mathematics, much more application in algebra or topology and things like that. While of course, I mean, in computer science application, they are interested in learning finite objects, right? Because what is an infinite objects in the
Very
world?
good. Very good. So now another more practical question. I mean, if are there, I mean, I'm not the chairman, but if are there more technical questions, I would like to listen the question, because now I would have a more practical question. Giovanni, what do you?
Yes, no. So I would simply like to ask if what you are studying is also or may have application in proof assistant for.
Yes, good question. Yes.
Okay, yeah, this is a really good question. So basically, for doing that, this is something I thought sometime I really didn't explore too much, right? So at least in my knowledge is completely new, but it would be interesting. So the idea, for instance, it is that you might have an analogous of this would be, rather than seeing models, right? So rather than see structures, what you see it is a collection of theorems, and from that you would like to recover back the axioms, right? So it would be a sort of reverse mathematics idea of implementing this, and why not? I mean, I think this would be an interesting project. And so basically, I mean, what is interesting it is that algorithmic learning theory is a lot within theoretical computer science, basically doing this version applied to structures. What we realized is that you have a lot of connections with mathematics, or at least, I mean, mathematical logic, right? So we are really stretching this area more to the mathematics side. I mean, the current work we are doing now, it is basically we were able to show that all of this can be phrased in a more topological and descriptive set theory sense.
Okay. So Letterio, you said that you have another question.
Yes, a more practical one. I was wondering if Luca can think about the possibility to prepare, for instance, let's say a short series of small talks, I would call pills, to give a basic introduction to all of us about this very interesting subject. For instance, because this was very nice, because we have learned to know you better, to know what you are working on. And it would be nice that you as an expert could teach us some mild foundation of your subject, giving, for instance, a series of short talk, let's say 3, 4, just maybe with a connection with philosophy, as you did at the very beginning, just to make more effective our collaboration.
Yeah, sure. I mean, I would be happy to. Sure, definitely.
Yes, we can think about.
Yes, you can think and we can discuss. Yes.
Yes, of course it would be very interesting, because I repeat it again that Luca is collaborating with us within the MARM project. So it's not that our meeting will be over in few minutes, but our collaboration continues. So I repeat it again. So if you have any question, or if you want to know more, you can of course exploit having Luca in our collaboration. So are there any other questions? So maybe I would like to ask you also another question. So at the beginning, when Martin, you have a question?
Yeah, I realized I was muted. No, I wanted to ask. I see that I think some of my questions I had have been answered by your last two theorems, or your because I wanted to ask, do you have some results like every structure is learnable? But I realized no, it's not the case. Or some characterization of learnable structures, and I see that you do have one such characterization. And then the other question I had was the a more practical type of question, where you given big data, lots of data coming from somewhere. Is the speed of learning determined upon quickly realizing what type of structure is that data? The machine being able to determine quickly that, okay, this data somehow fits this structure. So therefore, we can process this. So, I mean, is there a quick criteria where a machine can fit some big data into some type of structure?
Okay, so this is a very fascinating question. The point is, let me phrase it like that. So what we typically have in computability theory, the assumption, well, the main underlying notion, it is defining, producing a dividing line between computable objects and non-computable one, right? Where computable objects means being computed by a Turing machine, or there exists a computer program which do that, right? Typically in computability theory, we completely abstract away from the time complexity of this, which is of course a crucial notion in computational complexity, right? I also work, well, my main area is computability theory, but I also did, and I'm still doing some work in computational complexity, right? So for instance, what one can do would be, and it would be really interesting, so thanks for that, a computational complexity version of this. So for instance, now you would like your learning to be computed not only by a Turing machine, but a Turing machine which perform in polynomial time over the input the correct conjecture, right? And then, of course, basically you can do that in, I mean, people in logic like a lot hierarchies, right? So we do hierarchies all the time. So, and for instance, there is a stuff called the polynomial time hierarchy. And so if the learning fails to be at the level in polynomial time, you might ask whether it works at some level, right? In NP, in non-deterministic polynomial time, etc. So most of it is basically open. I mean, for instance, as soon as you add some constraints to the learning, to the learner, right? So the most natural one to us, at least, it is saying, okay, it's a Turing machine. But basically, you have multiple other options. I mean, might be a Turing machine with some time complexity limitation, or a Turing machine with some space complexity limitation, a quantum Turing machine, if you are in this kind of thing. Or it might be a finite state automaton, etc. I mean, of course, there are many, 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 many possible options for this.
Yeah, thank you.
Thank you.
Are there other questions?
Thank you, Prof. I just want to, can Prof hear me?
Yeah, sure.
Oh, yes. I just want to ask if there's any relation between this, let's say, an uncomputable structure or something that is not able to learn with the P and the NP things in computation.
Okay, so thanks for that. It's basically a follow-up of what I was saying before. So the idea it is that both the class P and the class MP fall inside the computable, right? So these are basically way of stratifying complexity inside the computable, right? So also the class of MP problems, in fact, are computable, right? All of them. The only problem with MP, it is that, well, for what we know, they seems not, generally speaking, MP complete problems, they seems not to be computable quickly, right? So basically you have a quick way of verifying if something is a solution, but you don't have a quick way of producing a solution for arbitrary instance of the problem, right? Where quick here means in polynomial time on the input that you receive, right? So you have this big, gigantic and $1 million worth problem for $1 million worth problem, which is basically asking whether the class P and the class MP are actually the same class. So whether it is the case that whenever you have a quick way of verifying a solution for a given problem, then from this somehow mysterious way, you are able to actually solve quickly a problem, right? So no one believed that, but it's still a really big open problem. And basically, we really know we have a lot of mathematical knowledge of why this is dramatically hard. But still, it is a separation of classes that live within the computable world, right? So all of them are just computable. Typically, in computability theory, we just look at more complexity, right? So we collapse all of the computable world in just one big class. We say it's computable independently from the time complexity. And then we say, okay, then what is not computable? So it is basically with abstracting it at all with respect to space and time constraints.
Right, thank you.
Thank you.
Can Elena make infinitely many mistakes? Because I realized you picked on the ones that make only a fixed number of mistakes, right?
Yeah, right, exactly. The first one, sure, but the second one, not, right? So take this example of learnability, right? In this example, you learn it, but you learn with an arbitrary number of mistakes, generally. So you always have, so this is not hard to construct, right? So the idea is somehow, suppose you would like to have a copy that you need a lot of number of mistakes to learn it. How this copy will behave? Well, the copy will be locally similar to A. Then it will expand being similar to B, then similar to A, then similar to B, then similar to A, then similar to B. Of course, at some point, eventually must stabilize to either A and B, but it might take a long time before stabilizing to one of the two, right? So basically you have learning, but you have copies that for a long time will resemble the other structure. So this is an example. For a more natural one, this is exactly what is happening with the very first example. This is exactly what is happening with, where was it? With, yeah, omega and omega star, right? So you have copies that for a long time will switch from resembling to omega and to omega star, right? And then only after, I don't know, 1 million points, eventually will look back to one of the two.
Great.
Other questions or comments? Well, so if no, we thank again Luca for the talk. And well, as I said, so the story is not over here, and of course we are going to plan something more for the future. So well, so
right.